Good afternoon, everyone. Welcome to TSDSI Tech Deep Dive TTDD 2023 conference. I am Sweta Singh and I am a session coordinator for session 3 Emerging Technologies for 6G. Now I want to introduce some hygiene instructions such as all attendees except the session speakers will be kept on mute, audio and video throughout the session by default. If you have any questions for the speakers, please type them in the Q&A tab. Questions to the speaker posted in the chat box will not be entertained. You may interact with fellow attendees live using the chats tab during the session. If you want to enlarge your presentation, please click the expanding arrow icon on the top right of the presenting screen. The tool is configured for HD video. You may switch to LD in case you are facing bandwidth problems. This webinar is being recorded and will be posted to TSDSI website within the next few days. Attendees may like to visit the exhibit booth of TSDSI in between the sessions to know more about our work. Attendees can use the launch facility for networking. The launch will remain open till the end of the conference. Now I want to invite Mr. A.K. Mittal as a session convener. Sri A.K. Mittal is associated with TSDSI as advisor with a special focus on standardization in wireless and wireline systems and handles standards related activities of TSDSI in 3GPP and ITUR. Hand over to sir.
Yeah, thank you, Shweta. Good morning, good afternoon, or good evening, as the case may be, depending upon the part of the world you are in. Welcome to all the distinguished participants, session co-chairs, keynote speakers, and panelists to the third session of TTDD 2023 with the title Emerging Technologies for 6G. Co-chairs for this session are Mr. Prakash R. and Ms. Priyanka De. I would like to briefly introduce them. Shweta, can you display their profiles? Yeah. So Mr. Prakash R. holds the designation of Scientist G in the Center for Development of Telematics, CDOT. He has been working as a researcher in the telecom industry for the past 30 years. His current interests include, among others, wireless networks, 4G, 5G, 6G, cloud computing, software-defined networks, open source, and standardization. He is an IEEE senior member, IET fellow, and ACM member, and also serves as chair in the study group networks of TSDSI. Detailed biodata is available on the website. You can kindly see that. The other co-chair is Priyanka De. She is a senior research engineer in the Center of Excellence in Wireless Technology, CIVIT, Chennai. She has more than 7 years of experience in research and standards. She represents CIVIT in TSDSI, 3GPP RAN 1, and ITUR Working Party 5D. At TSDSI, she has been the rapporteur of the study item on flexible duplexing and currently co-rapporteur of the work item on RIS. She was one of the recipients of the TSDSI Outstanding Technical Contributions Award 2021. She is currently Vice Chair of Study Group Networks in TSDSI. Over to the co-chairs, then Mr. Prakash for further proceedings in the session. Thank you very much.
Thank you, Mr. Mittal. Good afternoon, everyone. I'm audible?
Yes.
Okay, thank you. So, welcome to this session, TTDD. This is an annual event that TSDSI conducts. TSDSI is the SDO of India. And this particular session, as 6G is looming on the horizon, or shall we say 5G is now almost a done deal in terms of it is taken as a current technology. Most of them have taken it for granted that 5G can be built, will be used, and it is already widely being deployed. The activities have already started, hectic activities on 6G, early technology development, awareness, standardization, and scoping, and drawing the boundaries around what 6G should be. So since the whole conference is on 6G, there will be various other sessions which have talked about visions, which have talked about what is the KPIs and what are the boundaries or the interests of 6G as a higher level. Any technology when it has to be deployed, one is you need to set the targets in terms of the technical targets, the end user, the segments in which the technology can be used. But then anything you want to put together and get it working as an engineering community and a research community, we need to put together a set of working enabling technologies which together along with system integration makes the 6G vision come true. So today's session, this particular session focuses on what are the enabling technologies, what are the, these are not the final ones, but what are the aspects that are being discussed, where are the trends, and where are the research area interests. And ITU, as in the ITUR, there's already been a work and a report published on future technology trends. And that report is sort of the basis for the session, need not be restricted to that, but we have used that as an aspect to discuss. So we will discuss things like AI, we will discuss terahertz technologies, or is it positioning, is it the interface, air interface, advanced coding, modulation. So I will leave it to the speakers. I will not take too much time because we have a very distinguished list of speakers. The session is going to be in these lines. That is, we were going to have a keynote, 3 keynotes, and then we have a panel discussion. And I will introduce the speaker just before they start, as per our as per the order. So the first speaker for today is Jishnu, and Jishnu Aravindakshan. So he is a principal architect of technology in CTO's office at Tejas Networks India Private Limited. He has over 19 years of experience in the field of telecom. His present interests include 5G Advanced and 6G. He's been the chair of SG3 and a vice chair of SGN in TSGSI. He is actively involved in 5G standardization through TSGSI at ITU WP5D and as an individual member in 3GPP RAN 1 SA2. He has filed 18 patents and was awarded the Best Paper Award by IETE in 2006. So the remaining I will not read because most of the speakers are very distinguished and the briefs are very large. So I will now hand it over to Jishnu to give the first keynote for the day. Jishnu, over to you.
Thank you, Prakash. Thank you for the introduction. Thank you for TSDSI to offer me a keynote speak. So can I share the screen? Just a minute.
You may share. Also, if you may share your webcam as well, sir. Thank you.
So is it full screen? Am I audible and is it full screen?
Yes.
Yes.
Thank you. I have a few set of slides. So I just want to start off with what would 6G be enabling which 5G didn't do. So there are multiple usage scenario. I think 6 of them we heard yesterday from Dr. Xiong Jun as well, which is being discussed in ITU. I have taken one very prominent of the use cases, which is the immersive XR. So XR is already being discussed in 5G. Why it is still a issue in 6G? So if you see holographic communication, the key thing is that there are concepts like avatar, which is one of the thing which is being discussed as part of metaverse. There is also a consumer-friendly version of users, which is also being discussed. Maybe both of them would see some of those deployments in 5G. But there is also something called a professional quality digital representation of users in holographic, which at least I think that it would need 6G to enable it. Why is it different? So if you see holographic communication, it actually involves majorly 4 steps. One is acquisition, another is data estimation, third one is data fusion, and fourth one is post-processing. So if you see right now, we use what is called time of flight sensors like LiDAR to basically get the information. But in 6G, the idea is that sensing also get integrated into the communication network. So there is something called integrated sensing and communication, or joint sensing and communication. So this would allow you to have a much more immersive XR, and same holds for digital twin. So I
Vishnu,
would,
just a minute. I think the slides is not updating. All I see is a blank slide, a semi-blank slide. Yes,
is the screen
I
there?
got 2 of them now.
Yeah, it's
Unless you
two.
Okay.
Yeah, so I just moving around.
Okay.
Yeah, so that the second one is the real-time digital twin of cities or enterprise. So you can have a real dimensional view of, say, Bangalore city or Delhi city, and then both connected and unconnected objects are shown. So right now in 5G, we can only show the connected object because we have very good positioning in 5G. But we don't have this concept called sensing in 5G. So that would be the other thing which would come in. The second part is, can we have multi-sensory telepresence? So if I am having coffee at my place, can the person sitting on the far end can also smell that coffee? So something like that could be an extension of telepresence, which, for example, 5G is not able to provide. The third thing is that can we have a 4-dimensional holographic imaging, which is more about it fuses the information from MRI, CT scan, and make it more interactive so that the doctors could use it while performing the surgery. So this is one of those main use cases which I see driving 6G. If you go further in ITU, they have figured 6 usage scenario. These are like, basically they have looked into all the use cases and they have mapped it into 6 of the usage scenarios. You can see the green ones are an extension or expansion of the 5G usage scenario. The blue points are the new ones which are coming up. And as I mentioned, sensing is one thing, artificial intelligence is the second thing, and ubiquitous connectivity, which I think was discussed even yesterday, is the third item in that. So once this usage scenarios has been identified, there is also a corresponding capabilities which are identified. There are 9 capabilities which are extension of what was already there in 5G. 6 of them are completely new capabilities. As you can see, many of them are, even the parameters are yet to be defined. So all of them are under research phase. Few of them have been shown with a number. So for example, latency is like 1 millisecond. But you can see there is a range in bracket. So this is up for research. So if it can be improved, maybe we can get a better number mentioned in what is called the minimum TPR document. Once that minimum TPR numbers are known for each of the usage scenario, there would be corresponding capability numbers, or in 3GPP term KPIs, which would then drive what is the 6G technologies. As mentioned by Chair Prakash, there are few technologies being discussed. So I will go pick few of them and then spend some time to explain each of these. One is the modulation. So modulation, as you know, is sort of the basic thing for all communication stuff. So we are actually looking for like what are the basic modulation schemes which we can try for in 6G, which is like, so roughly we can say that 10% of the relative bandwidth is what you can use. So in sub-terahertz, if you are using sub-terahertz frequency, which is being considered, along with 7 to 24, in sub-terahertz, this would mean you can have roughly 20 to 30 gigahertz of bandwidth. So if I am able to do 64 QAM, so I will not be able to do 1 terabits per second. So if I am still with 64 QAM, maybe I need 170 gigahertz to get 1 terabits per second. So there are some experiments also on going to 16K QAM, especially in 7 to 13 gigahertz. So that would be one way to sort of increase the final data rate, peak data rate. So that's why if you see the numbers which have come from ITU, we have not put an upper bound on the number. The second part is coding. Can I have higher coding rate so that I can send more information bits? Can I have strong error correcting ability so that I can sort of improve the reliability? I don't really want to repeat. So I don't want to ideally use HARC or ARQ if coding can do most of the work. But if I do it, I would preferably do HARC rather than ARQ at an RLC layer. So that is another aspect which is being looked from a coding perspective, from a technology side. The third thing is waveform. As you are aware, in 5G, India had contributed to that pi by 2 BPSK with spectral shaping. So DFTS OFDM is a good technology for low PAPR. So is there something even better? One more issue which is coming up in 6G is we want to possibly take it to speeds up to 1000 km per hour. So in which case, maybe OTFS is a good technology because you can have a delay Doppler transform rather than the normal Fourier transform. So if you see from a OFDM perspective, you have basically orthogonal, bi-orthogonal, or what is called the non-orthogonal categories of waveforms or modulations which you can do. So these are all up for research. So there are multiple things which being discussed, which are UFMC, lattice OFDM, filter bank OFDM. So these are all up for research, and maybe a few of the speakers after me would be discussing those in more details. The next aspect is multiple access. So there are possibly two like categorization of this. There is something called orthogonal multiple access, or you can have non-orthogonal multiple access. So there is possibility for carrier sense based random access as a signal processing technology. So this is from the multiple access perspective. That within NOMA, there are multiple things like MUSA, PDMA, CMA, etc. So that's being considered from a technology perspective. The other research is on full duplex. Can we have better self-interference cancellation technology? And I'm sure some of the talks would spend some time discussing SIC technologies. There was a CLI introduced in 5G. So can that be used to avoid interference between base stations, between UE? So this is a topic of discussion already in release 19. The last aspect, the only way to really increase your throughput is either increase the bandwidth or increase the MIMO. So can we have extreme MIMO, but would it has to be at the same location, or can I distribute the MIMO so that you can have multiple locations, basically targeting the signal to a single user? And then can I use AI technology to sort of improve it? So that's one aspect of the eMIMO being studied. The other aspect is about holographic radio. So holographic radio is like very similar to RIS. So you are connecting the signal along with sort of an RIS type stuff. So maybe there are more discussion on this. So we need higher precision positioning and perception to basically make sure we can work on holographic radio. The other thing which is being like studied in NTT, mostly NTT Docomo, is about orbital angular momentum. This would be an ideal technology around in terahertz band. So this would allow you to sort of do the front haul, back haul, etc. using terahertz frequency. Here, basically, we have different phases, which basically allow you to, it's very similar to what happens in an optical domain. So you have multiple twists, what are called twists, which will allow you to keep different signals orthogonal to each other. So in May 2023, very recently, NTT Docomo was able to show sort of 1.44 terabits per second using this OAM on a point-to-point basis. So this looks promising technology for getting into terabits per second range of data rate. The other aspect which is quite commonly discussed is RIS. It's also called IRS, Intelligent Reflective Surface. industry somehow seems to be more interested to call it RIS, Reconfigurable Intelligent Surface. So this again allow you to sort of improve the SNR, especially for NLOS area, increase the cell capacity. I'm sure Professor Chandra, etc., would be explaining it in detail in the later part. Hopefully, this should help you to improve network coverage and improve cell edge performance. The other aspect is about terahertz technology. So we are talking about sub-terahertz being used for communication. Most likely, it will be for backhaul, fronthaul type application or between devices to device communication. So the key problem there is how do I create pencil beam terahertz radios, which is basically can I use some ultra massive MIMO structures to basically at small size to provide high beam gain and maybe do whatever the inter chipset communication or even a backhaul fronthaul sort of communication. This would, so basically we would need very high directional antennas and preferably a steerable antennas at terahertz to form the beam forming. The second category of problems are about terahertz transceivers. So can we have fundamentally operated, sub-harmonically operated transceiver architectures? So this is another issue which is being seriously researched. Can we have receiver architecture which are tunably band filters, etc.? The last aspect is about RF and baseband processing. So is there some, so for example, resonant tunneling diodes and Schottky barrier devices. So these are commonly used also in optical. So they are being looked up for as a terahertz transceiver. Even the process technology may have to move from silicon to gallium arsenide, indium phosphide. So these are some other terahertz fundamental things which are being studied. The other aspect is about the baseband processing. Can we provide, how do I do ADCs where we unlock to digital conversion? How can I do very high level of ADCs? So these are broadly the technologies being discussed in 6G. You can read more of that from the ITU paper which Prakash was mentioning. So roughly this covers the major aspects of the technologies which are being discussed, and that sort of concludes my talk. And I can take questions later after other keynotes are done. Thank you, Prakash.
Thank you, Jishnu, and thanks for keeping the time. Are there any questions? Maybe in the spirit of time, we will bundle it towards the end. The next speaker is Professor Rahim Tafazoli. I hope I got the name right. And Professor Rahim Tafazoli is the only Regius Professor of Electronic Engineering. He's a professor of mobile and satellite communications, and he also serves as the director of Institute of Communication Systems, ICS, and the director and founder of the 5G Innovation Center and the 6G Innovation Center at the University of Surrey, UK. He has been active in research for over 30 years and published more than 1,000 technical articles, and is the editor of 2 books and is the chief editor of Wiley's 5G reference book. He is a fellow of Royal Academy of Engineering, fellow of IET, and fellow of WWRF Forum. Okay. He's also been a technical and strategic advisor to many of the mobile companies, and he served as a member of UK government DCMS task force on the diversification of telecom equipment equipment providers ecosystem. And he is an expert representative on the UK Space Agency to European Space Agency on the 5G over satellite. He also has served as a technical advisor to the Mayor of London, Boris Johnson, on the London Infrastructure Investment Plan for 2050. Okay, so thank you, Professor Rahim, for accepting to be a part of our TSJSI workshop. We are happy to have you as a speaker, and I will hand over the floor to you.
Thank you very much, Prakash. It's good to see you online. And let me see, can you see my presentation?
Yes, we can.
Oh, excellent. Thank you very much, and good day to everybody. Previous speaker gave a very good, thorough overview of what is expected from 6G and how it is different from 5G. So I will try to share with you some solutions, not all the solutions, but some solutions that we have been working on towards 6G. First of all, I have to say that we were the first in the world to start 5G Innovation Center and the first in UK to do 6G Innovation Center in 2020. We work very closely with industry, with major mobile operators, manufacturers. Our job as academic is very simple. It can be summarized in one sentence, and that is, what is the arts are possible? And we share that with our industry partners. And this was recognized by Royal Academy of Engineering as the best research center in UK working with industry. So we're still working on 5G, especially on 5G Advanced. There is a lot of features in 5G, which is very rich and capable features, and we should never forget that and jump towards 6G. And in parallel, we are working, researching on advanced technologies towards 6G. So what is 6G from our perspective? And when I say our perspective, I mean not only us as academia, but also our industry partners. We discussed this with our partners. We said, what should it be 6G? Because 5G and 5G Advanced through all the releases to release 19 is very powerful technology and very flexible. So what should it be 6G? They gave me these 3 points. They said it has to be the future technology in 2030 plus, has to be extremely environmentally friendly and energy efficiency, for example, from that point of view. It has to solve societal problems and also helps the economy, and industry has to make money out of this. So we said, okay, we look at integrated communication and sensing. So that's what we said in 2020. And then we had to map all of this into some technologies. We said, okay, how are we going to be environmentally energy efficient and friendly? We know, for example, 5G energy per bit is more energy efficient than 4G and previous generation system. But every generation is about 20%, 30% more energy efficient. We set this challenge upon ourselves. We said, can we do some technologies that it would result into, say, 300%, 400%, 500% energy efficiency rather than 10% or 20%. The system has to be very reliable because everybody, for professional and private life, they rely on this wireless connectivity, security, privacy, and trust. And digital divide. This is a societal problem. We need to solve this digital divide and make broadband available to everybody. It doesn't matter where they are. And we have to do all of this with the full consideration of the full 5G capability. So we don't repeat and reinvent the wheel and label it as 6G. Industry said, let's focus on a use case that has a very clear business case, that they can make money out of that. So we came up with this 4-dimension video, which we refer to it as teleportation. And previous presentation, I was talking about the metaverse or holographic. So I will discuss about what we mean by that a bit later on. Intelligent surfaces, sensing and sensing technologies. And we said that the future 6G should be a network of networks. One technology, whether it's 5G or 4G or 6G for terrestrial, it cannot really economically and energy efficiently serve all types of environments, from open areas, rural areas, indoor, outdoor areas, etc. So we came up with, on the left-hand side, with this 3-sided shape. In 2020, we said we need to solve the problem of the coverage, and especially the quality.
Professor Rahim, just 1 minute. I think some of the people are having, the slides are not changing.
Oh, is on slide number 5.
Okay, we see. Okay, now it's come.
Is it coming?
Yes.
Okay. So in 2020, we came with this. We said 6G should solve the problem of coverage. It has a variety of different sensing information that it needs to be embedded into the communication. And we said one more thing, which is different from 5G, is a high quality time synchronization. So 5G was, for the first time, introduced low and guaranteed delay. So what we say 6G should bring is time synchronization, high quality time synchronization. And we use AI and ML wherever we think that it would add a benefit compared to conventional techniques. So in 2023, it was presented again, the same thing. The blue ones are the 6G, and you see it's integrated communication sensing using AI, and also ITU is addressing ubiquitous connectivity. So the same thing as we said in coverage. So I'm very pleased that 3 years before ITUR came up with these objectives, we managed to get it right and carry on with our research. So we divided all of this into a number of technology research, which I'm not going to, because of time, I'm not going to go through them. And the previous speaker mentioned most of these technologies. So to summarize what we do in one page is network of networks. We believe the satellite communication mega constellation is very important to be fully integrated and complement the terrestrial system. Another challenge is, can we provide direct satellite to user terminal directly without extra antennas, and the same phone that we use for terrestrial system, we use it with a satellite. So it's direct to the phone, direct to UE. So that's one challenge, and we are looking at the technologies for that. Another challenge with respect to coverage is, how do we, what is the role of intelligent surfaces? And we built some based on the holography and material, 2 different reconfigurable intelligent surfaces. One is more intelligent, the one on the left-hand side is more intelligent than the other one. And I will explain a bit later what is so special about this. Time synchronization is very important for cyber and real-world interactivity, as well as for synchronization between driverless cars and manufacturing, and also for holographic sensing and interactivity. On the sensing side, we are looking at sub-terahertz to look at the location with sub-millimeter accuracy and real time. And other sensors that we are considering is, in addition to audio and video, which is current technology is based on, which is 2 of the human senses, we are adding other human senses like touch, taste, and smell. And we are heavily working on how we can capture the real touch, natural touch, and transmit that one together with the virtual reality, with the time synchronization, and then with the accurate locationing, and etc., with the radio imaging, and we provide a kind of teleportation. But I'm not going to focus on this teleportation too much today, but my main focus is here is coverage, which I believe that it would be important to countries like India as well. So sensing, many people talk about it, but effectively sensing give an eye to the system. Most of the system technology or networks so far we try to sometimes blindly detect things, estimate things, the signal processing, net protocols, and etc. Whereas the sensing, it gives an eye, and it helps the all layer of protocol stack, from radio, from network protocol, from the system, from the spectral efficiency, as well as provide a new, more intelligent type of services. So there are 2 types of sensing. One is the sensing information that network can utilize to manage itself better in terms of resources, in terms of quality, coverage, capacity, quality of service. Another level of sensing, which I've already mentioned, is the ambient information, including the 5 human senses that needs to be captured and to be integrated in communication system. I will skip this one because of the time. It shows a variety of different sensing which network can use to manage its operation. So let's talk about coverage. Coverage is very important to us, to our, as well as our industry partners. The question is, can we simultaneously increase the coverage and capacity and energy efficiency? Can we do it simultaneously, not one at the expense of the other one? This is a 40-year-old problem since the beginning of the 1G. So coverage challenges are outdoor to outdoor, outdoor to indoor, indoor to indoor, as well as open areas. So that's why we say it has to be network of networks feature system. So let's look at a little bit deeply in the coverage imbalance. There is a lot of dead spots which stops providing high quality broadband coverage everywhere uniformly. And this shows the typical coverage of 4G, and blue lines shows areas when the signal to noise and interference ratio is very low, therefore there is low data rate can be supported. The red bits are the ones that we can provide higher data rates. As you can see, the coverage is not uniform, even for outdoor environment. So one thing that people are talking about is densification. Let's densify and increase the number of sites. Densification has problems, and it gives answers to some limit. Beyond that is become a bit of more problem. One of the problems is it creates more cell edges, the densification. And more cell edges, more interference, and there's some study was done it says that the rate of increase of the densification, about twice densification, 4 times, 8 times, 16 times, all the way, etc. And it's a rate of increase of the 5 percentile coverage. It gets worse. And for example, 95%, it improves. The 95 percentile of the cell coverage improves until there's 4 times densification. After that, it degrades. So we have to be careful when we talk about densification. Densification is not ultimate solution forever. So as much as densification we can do. So we have to be careful up to what point it gives benefit, at to what point it doesn't. So we work on this problem, and there's a publication that we have submitted, and I think is available that people can read more detail. We said normally if you have like a sectorized system, as you can see here, like a 3-sector and it's 7 cells, and if we rotate this 60 degrees or 120 degrees, this radiation, which is electronically, and we keep rotating it like this, and the bore side will overlap with the side lobes where the signal to interference ratio is low and the antenna gain is lower. So when we rotate it, everybody will enjoy the maximum gain of the antenna. How fast we rotate it and how much we rotate it depends on the system designers. If we do this, as you can see, the blue lines are extremely reduced, and more red areas appears. So that means more uniform coverage. So we've done a huge amount of simulation using 4G, SISO, MIMO, different frequency bands, the bandwidth, and different scheduler. So if you have a static sectorized cell, this is the coverage. There's a 3-dimension coverage. As you can see, some areas, the average throughput is extremely low. And some areas, the throughput is very high. But if you do this cell sweeping, the coverage becomes very uniform. We are not increasing the capacity, I have to mention, but what we are doing here, we are spreading the capacity more uniformly across the coverage. So it's a very simple solution with a very high gain. So I'm not going to go because of it. And because of this, the system can use high CQI, so high level modulation and coding, as you can see with the red ones, as opposed to the blue ones. I have to say that when we are not increasing the capacity, we are just spreading the capacity more uniformly over the coverage area. And let me just summarize this aspect. In addition to increasing and making the capacity more uniform, we can, for the same coverage and same quality of coverage, depends on different configuration, we can 30 to 60%, we can reduce the number of cells, the number of sites. Power consumption, based on the study that we did, is about 26%. We can reduce the power consumption. And it can be included in 3G, 4G, 5G with MIMO or with massive MIMO or even 6G. So the principle applies to MIMO and millimeter band as independent of the frequency band. But what is another thing is important because of the sensing, when the beams rotate, what does it remind you? they should remind you of radar. And radar radar function is part of the sensing in 6G. So simultaneously, we can do sensing, we can increase the coverage, and we can decrease the power consumption at the same time. So another technology is transmitting or reflecting intelligent surfaces. And it is more transmitting for outdoor to indoor or indoor to indoor. Reflecting is indoor to indoor or outdoor to outdoor, etc. Or simultaneously can do transmit and receive these sort of technologies. I said that we built some of these, and we demonstrated about 3 years ago in November 2020 in a real environment. But what is important here, I want to show you this number of unit cells, for example, this for reflective intelligent surfaces, 11,000 unit cells, and it always reflect 45 plus minus degrees. The gains we got is 20 dB. And more importantly, it is zero input power. So we get 20 dB gain to provide the coverage with a zero input power. And it is wideband. As you can see, it's 400 megahertz bandwidth. So when I said about 300%, 400% or more energy efficiency, because energy consumption is directly related to the coverage as well as frequency band. So if we can provide coverage, say 20 dB or 10 dB with a zero input power, that's a huge saving on the bandwidth, on the power consumption. Another intelligent one we did, which is the reflected beam, actually follows the user. It's more intelligently, it follows the user, and we tested this one. And the power that we need here is just very low power electronics, as you can see in this box, which says ICS. But it doesn't have amplifiers, it doesn't have filters, it's not an antenna either. And that hugely reduces the energy consumption, at the same time provide very good coverage. We have done one step further, and we implemented this transmitting into the glass. So for single glaze glass or double glazing glass, and it's see-through and transparent. And we tested this one about 9 months ago in our building. And that is, you can deploy this one on the windows of the building, on the car doors, or on the trains, and etc. Wherever you have windows, and provide that huge amount of gain more energy efficiently. Another important element of the 6G, we believe, is 5G. So is a satellite. So 5G for satellite with the mega constellation is trying to bring mobile broadband, Internet of Things, as you can see, many applications. For 6G, it is not only about the coverage, but also services that satellite can provide, like positioning, navigation, time, key distribution, providing direct line for UAV or line of sight, and we are researching on satellite to UE, direct satellite to UE, and Earth observation. Earth observation is part of the sensing. So we're sensing the information on Earth for a number of variety of different applications. Could be agriculture, could be national land security, it could be many, many different things. So the satellite should not just be looked at as providing coverage, but also some services that it is only possible using the satellite. So direct to UE is a big challenge, technical challenge. There are people, in addition to what we are working on, there are many people internationally working on this direct to UE. And some people using very simple approach to this. For example, you see AST system has a big antenna the size of a tennis court for the satellite in order to provide the link budget, which is about 64 meters squared antennas. But we want to do a little bit more intelligent way of providing the link budget to the UE with a small antenna gain. So the concept that we introduced, and we are researching on that, we said if you have a mega constellation, you have a large number of satellites. Why can't the satellites in a space where they have inter-satellite link or they don't have inter-satellite link form a mesh network? Like UE to UE, or you can look at it as terrestrial equivalent, like a distributed cell-free MIMO. So why can't we have cell-free or distributed MIMO in a space? So they collaborate and they enhance the received signal together. And we have done some publications in PMRC last month, and we have more publication in Globecom is coming in Kuala Lumpur. As you can see, if we have, say, we use a Starlink constellation, only constellation, in London, in Guildford, where Surrey University is, we can see 28 satellites for about 10 to 14 minutes. So 28 satellites, if you look at one satellite or up to 5 satellites or 10 satellites, all the way to 28 satellites, the link budget increases and therefore the capacity will increase. So this is instead of using big antenna arrays, the cooperation and collaboration, it can give you that link budget for direct to UE. And we have actually tested this concept for a variety of different frequency bands and different bandwidth. And I'm not going to go into detail of this. Sometimes we have perfect or imperfect channel state information between the satellites. So this is still ongoing research, and I think in researchers in India, it will be a very useful research area that to work on. There's a lot of research challenges is still yet to be addressed. So we have also this network of networks. We have a national program. It's called TUDER, which is Towards Ubiquitous 3-Dimension Open Resilience Network. So open networking is very important strategy in UK, and we believe that 6G should be as open, not only like Open RAN, but also the rest of the network should be open so we can get more vendors, small and large, can be in the ecosystem and provide solutions. So this project is about 8 universities. We are leading that together with over 16 companies, international companies. We are working on all aspects, satellite, terrestrial, etc., and try to do some advanced technologies for this 3-dimensional network. So the goal is to enable single integrated terrestrial and airborne and space platform in form of 3-dimensional networks, security, resilience, and being open, that we can provide universal coverage outdoor and remote areas as well as indoor urban areas. So the principle that we are following in TUDER project is based on this fact. We know that future system will have sensing. Sensing provides eyes to the network. It does things more, signal processing, network protocols, network management with extra information that is the sensing provides. Semantics and AI effectively gives a brain to the network. It can learn and it can develop. Time synchronization provides a heartbeat for the network, and virtualization software from hardware separation. It gives us kind of freedom. So if you look at this principle, it is like a human being or a being, a living being that from childhood it learns and evolves over the time. So why don't we design the future networks that it can learn and become more sophisticated with more functionality over time rather than trying to implement everything from the day one. So this is a basic principle that we are following, and we are trying to look at the open RAN and open core and open transport with the satellite and terrestrial, and all of them will be based on distributed cloud native platform architecture. We are also taking this research further, and we are looking at semantic communication and sensing to further reduce the bandwidth consumption and energy consumption, and use intelligence and AI wherever it is makes sense compared to traditional technologies. So this is a large project, and we are about less than 6 months into this one, and we have further 1.5 years to do more research in this area. And the research is done a combination of experimental research using a test bed that we have, and also computer simulation and etc. By the way, I'm pleased to say that our test bed, which is on the campus, is a large test bed, is currently connected to IISc in India, and we are doing Open RAN research with Professor Harry in IISc. So thank you very much. I hope it was useful to share with you our perspective of 6G, and I believe that it is very much in line with ITUR as well, but we start about 3 years earlier. I had more to talk about, especially on the sensing, but because of the time, so I just wanted to reduce this presentation to the coverage and technologies that can simultaneously provide good coverage, energy efficient, high capacity, and simultaneously. Thanks very much for this. I'll be more than happy to.
Thank you, Professor Rahim. That was a really enlightening talk, and thank you for putting all the key technologies into something that is understandable, and we now start seeing an animal rather than its parts, and it was a very new concept for us, and it was very happy to hear it. We're just a little short of time. I would have loved to take some questions. We have another speaker here, so we will hold the questions to the end. Maybe at the end of this session, jointly across all three speakers, we can try to take questions. So the next speaker is Mr. Hideaki Takahashi. I hope I got the pronunciation right. Mr. Hideaki is currently the Senior Specialist Standardization in Nokia. He has about 23 years of experience in telecommunication and automotive industries, including NTT Docomo, which is a Japanese mobile network operator, and Denso, which is an automotive supplier. He has been working on mobile technology telecommunication standards since LTE onwards, and as a delegate in 3GPP. He covers the RAN architecture, RAN WG3, radio protocols, RAN WG2, and RAN project management with the PSG RAN. He is currently an SA1 delegate from Nokia, and he works on the service requirements and system architecture design for 6G. Over to you, Dr. Hideaki.
Yeah, so thank you, Prakash, for introducing me, and thank you also for TSCSI for giving me an opportunity to be present here. So let me share my screen. And also let me also share my slides. I hope that you can see my the screen, but please let me know.
Yes,
Yeah.
we
Okay.
can see.
Okay. So today I'm going to present the technology to enhance radio access network for 6G. So um, so my plan is to share Nokia's 6G vision, and then I will present the key technologies for the 6G radio access network. So first, let me briefly explain what Nokia is envisioning for 6G. So, so we Nokia believes that in 6G era, the digital, physical, and human worlds will become far more integrated. So 6G will profoundly transform our world, and in that process, liberate our innate human potentials. And next slide shows the wireless system design principles for 6G. So yeah, I'm sure that you will be familiar with this content. So this is a use case already supported for 5Gs and also for key performance indicators for each the use cases, EMBB, and massive MTC, and URLC. So we think that these use cases and the KPIs are still valid and important for 6Gs. And of course, 6G should support higher capabilities than 5Gs for these key KPIs, like in this slide. So on top of that, we think that the 6G can go beyond and to create new key values which is not supported by the previous generations. We think these are the sustainabilities, digital inclusions, and security and privacies. So for sustainabilities, 6G should support 10 times capacity increase, but at the same time, also support 50% power reductions compared to 5G. And digital inclusions aims to address accessibilities, affordabilities, and consumabilities. And security and privacy, of course, these risks require higher levels of controls. So these are the 6 visions we Nokia is envisioning. And next, let me move on to the key technologies for 6G radio and radio access network. So this slide shows 6G work core. I mean, this is the key 6G radio and radio access network technologies to empower 6G Starship, like in the movie of Star Trek, if you are familiar with. This immersive communication, air interface, and architecture enablers, extreme energy efficiency, and AI natives. So as already explained by previous speakers, these are the key enablers for IMT 2030 capabilities recently discussed in ITU-R. And immersive communications will be covered by the other speakers from Nokia in the next session, session 4. So this presentation will focus on the other 4 enablers. So the first is AI interface. So why 6G radio? So this is a very good question. So let me answer to the question with key building blocks in this slide. On performance side, 6G should support very high data rate, no matter where you are, and lower latency. These are the central pillar of new emerging services, like immersive communications. In addition, enhanced uplink coverage targeted for all data rate from low to higher data rate is more important to support the um, um, so to support the change of our life, how our mobile and IoT devices are used in 6G era. And on spectrum side, it is also important that the 6G can support better performance than 5G Advanced using the new spectrum for 6G, for instance, 7 to 15 GHz as a candidate. And the new spectrum coverage should cover the larger area with a macro cell grid. And apart from the radio performance, scalability and optimizations are key motivations of 6G radio. Energy efficient network and device are top value creation for us to tackle with the sustainable environment globally. And how to use the available spectrum in an efficient and intelligent way is is an emerging demand given the diverse spectrum allocation from low to higher frequencies. And also, smooth migration to new 6G network is a fundamental feature for operators to ramp up new 6G services timely and cost efficiently. And AI machine learning, this should also be integrated natively from day one 6G services. And last but not least, 6G radio should be lean and implementation friendly, learned from the current 5G design. And next is the architecture enabler for migration towards 6G. Nokia is envisioning a single standalone architecture as in this figure. For 5G, non-standalone operation was supported in addition to standalone. So unless network migrates directly to 5G SA, network needs to operate both NSA and SA. So from the experience learned from migration to 5G, we believe that the single 6G architecture can leverage all of the 6G radio features. Single standalone operation makes energy efficient and implementation friendly. And as a design principles, 6G standalone should work in cloud native deployment and should be trustworthy. However, you may wonder if the smooth migration to 6G is feasible without NSA. Please let me try to answer to the question in the slide. We believe that the spectrum sharing with 5G and 6G in a dynamical manner plays a key role, which we call multi-radio spectrum sharing, MRSS. The left figure shows how MRSS is used in 6G standalone architecture. In the beginning, 6G coverage with the new 6G band, for instance, 7 to 24 gigahertz, as in this right figure, I think this is likely to be the hotspot coverage. The existing frequency band to provide the wider coverage, maybe FR1, is used together with the new 6G band. So carrier aggregation is used to aggregate those two bands in order to provide the continuous coverage and capacity boost. And hence, carrier aggregation should be supported for 6G from day one. On the other hand, the existing coverage band is used also for 5G to accommodate legacy 5G devices. And the question is how to coexist and 6G in the coverage band. Here, MRSS is expected to play that role. As you may know, that the dynamic spectrum sharing is already supported for 4G and 5G, which is in fact less efficient, and so one of the issues to migrate to 5Gs. Enhancements were introduced for DSS in later 5G releases in 6G, but of course, all of them are optional support for UE. So MRSS should achieve much higher efficiency than 4G and 5G DSS, and should be supported for all UE from day one. So uplink carrier aggregation in standard operation is also essential to enhance uplink capacity and should also be supported from day one. So with this approach, we don't have to support interrupt aggregations like NSA for 4G to 5G. So and with this concept, Nokia believes that the single standalone architecture enables operators to migrate to 6G smoothly with assistance of MRSS. So next is the extreme energy efficiency. To set the 6G goal, let us first take a look at 5G. The figure here shows the power consumption of a single 5G carrier as a function of load, assuming a 100 MHz bandwidth, the 64 transceivers, massive MIMO radio unit, and the power scales down with the load for the power amplifier because of the DTX feature. So PA is turned off when there is no traffic. So we then get a step drop because of massive MIMO muting. However, the digital power remains even at zero load until the cell is completely shut down. So if we were to look at 4G, the capability is about 20 times less, and the energy efficiency at peak load is 10 times less than that of 5G. And so the peak power consumption is almost a half. However, operating the same way as 5G, its power will also go down with load. In fact, 4G could actually be more efficient at low loads because of lower digital power consumptions. 5G has not been designed to be superior for all possible load levels, even though it is 10 times more energy efficient at peak load. So with 6G, we should try to achieve three things as we scale up the capacity by as a factor of 10 to 20 times using larger antenna arrays. First, we should aim for much lower energy consumption for at least the load level below the 5G capacity level. Second, we should try to achieve a graceful reduction of power to zero power at zero traffic. Third, we should try to achieve an exponential drop in power consumption from the peak power as the load goes down. Each drop here is tied to some knob that is activated. So I will touch upon some of the key RAN technology areas that requires standard changes or the ecosystem to work together. So the first RAN area for energy efficiency is hardware centralizations. the classic architecture is shown on the left. The base stations are distributed, and the cooling requires climate control in each site that consumes a lot of energy. On the other hand, with centralizations, the cooling is done across multiple servers in the same place. The power utilization efficiency is higher than the classical architectures, and the cooling gain can be achieved by the centralized implementations. And on the other hand, maybe one potential drawback of the centralization is the energy required to transport the information to the central site for processing. Nevertheless, we think that the total power saving gain by the centralized deployment outweigh the drawback of the energy for transport network. And in contrast to centralized deployment, maybe there would be a potential study area to deploy RAN functionalities over the heterogeneous cloud servers. RAN over cloud network may reduce the network operational expenses and enable rapid introduction of new services. On the other hand, it is not energy efficient to implement signal processing intensive physical layer functions on CPU and GPUs. So RAN accelerations with ASIC would require 10 times less power than CPU and GPU. And the other solutions to switch on and off functions and hardware is needed. For instance, according to the traffic load, aided by AI and machine learning automations. So further study would be needed for the cloud-native approach in terms of energy efficiency. And the other aspect is the network exposure and the control also play a key role for sustainability as a service. So as you know, that the lower CO2 emissions and the sustainable services are visible to us in some services already, like Google Flights and Uber, etc. So likewise, 6G networks should also be able to expose such energy efficiency and sustainability information to the application, so the users can utilize these informations and contribute to the sustainable societies. So we believe that it is a brand new and unique value creations that 6G can offer to our life. So the last topic is AI native. So the roadmap towards 6G. The first row shows the classical transceiver and the receiver architecture as we are using in 5G. So in 5G advanced, we can use AI and machine learning to further optimize the performance for individual blocks. For instance, channel estimations with a reduced number of reference signals. And in the second step, we are exploring the opportunity to simplify and optimize the performance by combining several blocks in a so-called deep RX approach. A better performance is possible because with separate blocks, some information is lost at every interface and handovers. By combined approach, we can jointly optimize across multiple blocks, retaining more information in the process, or resulting in a more accurate outcome, as this is only at the receiver side. So no additional translation is required, and hence such a capability will be possible even in 5G advanced. And further improvements are possible by also applying machine learning in the transmitter side and let the two endpoint self-run the most efficient communications. However, this requires new air interface standards that allows the feedback between the transmitter and the receivers. So we think this is a concept for 6Gs. And for these deep learning solutions, of course, it requires a computational capability and hardware accelerators is needed. So nevertheless, the future line rates to be supported can support the processing required for air and machine learning, we believe. So So this is the last type. I hope that this is still on time. So if we look at the future beyond 6Gs, how the AI native communication and the application looks like. So a long time ago, the technical problem for communication theory was to transmit the communication symbols accurately. So the further the level, how the precisely the transmitted symbols convey the desired meaning and how the received meaning affects in conduct in the desired way. These are thought as semantic problem and effectiveness problem, and these are not considered as engineering problem. But in 6C era, maybe this will be changed, and semantic and effectiveness aspects will be relevant to the and to the engineering problem with AI and machine learning applications in the endpoints. Maybe this will be happening after the introduction of the 6Cs and later in the 6C era for the futuristic scenarios. So that concludes my presentations. Thank you also for your listening.
Thank you, Dr. Hideaki, and thank you for keeping the time. And I think we'll squeeze in one question per speaker. Maybe I'll ask the first question to the first speaker, Jishnu. One of the question I saw on the chat box is that what is the data throughput you expect required for a 4D hologram? Okay. What sort of capacities do you anticipate which will give the load onto the system?
Yeah, thank you, Prakash. Thank you for that question. So basically, if you see how the holographic communication is represented, so you basically have what is called a point cloud data. So each point is actually sort of representing what you can say as a video frame, and you can have say something like 100,000 points in that point cloud, or you can scale it up to 1,000,000 points per frame, and you can have 30 frames per second. So if you directly take it without any codecs, without doing any codec part of it, it would come to close to 3 Gbps as the bandwidth you need. So this is assuming no codec. So if you assume codec, so there are what are called the V3C codec and VPCC codecs, which are basically takes a 3-dimensional representation, first convert it to 2-dimension, and then basically do H265 or H266 codec. So that portion you could basically even bring it down to as low as 1 to 6 Mbps, but these are mostly for a consumer level thing. So that is what I was saying. 5G itself would be able to do it. The other dimension, which is about, am I audible or something has frozen?
Yes, you're audible. Hello?
Okay, yeah, I think something happened with the video.
Yeah. But you're audible. Clear.
In that case, you can for 5G that's what is being discussed. So 1 to 6 Mbps is what it would be possible. So if you want to increase your like what we have the 4K or 8K television, similarly, I'm expecting hologram also should have similar higher resolution. It will accordingly scale. So worst case, it will be 3 Gbps if you have to do 30 frames per second, 1,000,000 points. The other bigger point is if I have to basically use my existing phone to do the holographic compression, either based on that V3C codec or VPCC along with H265, I would take 170 millisecond to process the hologram, which can be brought down to 70 millisecond if you have an edge. But other way to see this is if you have a large communication thing, maybe we don't have to process, we don't do the codec itself, send it as is from the communication medium, and then maybe the handset can decode it faster and reduce the latency. So if latency is also a concern, other way is like hand it over as a communication problem and then don't do much codec. So that's the answer to that question. Thank you.
Thank you, Jishnu. I hope it answered the question to the person who had asked. So one question to Professor Rahim, there was this one, that is, what is the, there was a slide which said network sensing versus situation sensing. So what is network sensing? Some sort of example, user level sensing or ambient sensing versus network sensing. One is, what is the meaning of network sensing? Second one is, what is the cost of the RIS? Whatever you showed an RIS that was put up in the proto. So what sort of cost do you anticipate? These are two questions.
Yeah, the cost is for RIS is not expensive, because the material is not expensive and depends on the size that you want to make and the number of unit cells. But the cost is, I answered this question on the question and on the chat, is based on the economy of scale. If it gets largely deployed, the cost will go down. The manufacturing cost will go down. And it's substantially, it's less expensive than putting another base station. It is a lot less. And the maintenance is very, very low as well. So if you look at all the cost factors. So that's for the RIS. For the network sensing. Network sensing, if you, I skipped that slide quite a lot. For example, if you have, on my slides, it said that if you have driverless connected cars, they are all converging to a roundabout, a square, that causing traffic congestion as well as huge interference, for example. Well, because all the cars are wirelessly connected. So if you have a camera, you don't need to transmit any signal. Then you see the traffic is gradually building to get to that congestion situation. You have plenty of time to manage the interference before you get to the state that is heavily congested. So this is a camera. It could be a sensing. It just gives an eye, I already mentioned, to the network to manage the interference. Another type of sensing is, if you know where the traffic is, when you have beamforming, instead of trying to do to detect and estimate where the traffic or the user is moving, if you have a camera, you know where the user and the traffic is moving, and therefore you can steer the beam minimum time to the direction that the user or the car or the vehicle is moving, rather than trying to blindly do channel estimation, antenna tracking, and beamforming, and etc. If you change the RIS is kind of a sensing. We sense electromagnetic waves. We engineer the phase and amplitudes to make a bigger signal, larger signal power, and redirect it to the location where there's a blind spot, for example. So other things sensing that people are referring to is like position sensing, direction of movement sensing. If you have like a radar, you can see the objects, you can detect the objects, which the object could be human, it could be another robot, or it could be a car, or whatever it is. And that gives better information used together with AI or ML and etc. to manage resources, to manage mobility, to manage so many things. So this is the information sensing that network would need to manage resources and services much better. Then there is another level of sensing, which is a human sensing, which I took it to the extreme case of using sensing and transmitting all the human senses, all the 5 human senses, together with the noise, ambient noise, the ambient light, ambient whatever information is around the user to be transmitted. And this is our version. I didn't talk about this one, but this is something I will refer to it as teleportation.
Okay. Thank you, Dr. Rahim. And one question, I think this is the last question that we'll have to Dr. Hideaki. So, Dr. Hideaki, you had mentioned that SAS, the primary, do you not see NSA mode when you transit from 5G to 6G? And you also talked about energy efficiency, your comments on using general purpose. There's a lot of talk of open RAN, open computing, and so on. So, what is your comments on ASIC versus general purpose computing as we go forward? How do you make it open, but the balancing between ASICization and using general purpose computing platforms or FPGA in between? Dr. Hideaki?
Sorry, Prakash, is this a question to you?
Yes, it is a question for you, Dr. Hideaki.
So,
so the question, I'll repeat the question. You said, when we start trying to do energy efficiency aspect, one trend we see is trying to use generic computing platforms. And if you use generic computing platforms, they are deemed to be less efficient than ASICs. And how do you balance the openness trend versus the ASICization of the?
Yeah, of course that So I think that generally, so of course that there would be the is it a trade-off, but I think that so generally the computing processing enhancement in future could also in the end contribute to the energy saving. So of course that if the processing is completely faster, of course that there would be the opportunity that that we can save the CPU power and the resource in the time domain. So that's why I think that this the computing processing and the capability enhancement will also contribute to energy saving in future. But of course, this is a trade-off between the service and the computing resource and load required for the target use case.
Okay. Thank you. So we would love to have more questions, but I think we have a panel discussion and we are about 5 minutes running behind. So I think we will now switch to the panel discussions. Okay. And we have maybe invite the panelists onto the chair. So we have the first panelist we have is Professor Chandramurthy. Professor Chandramurthy is a professor in the Department of Electrical Communication Engineering at the Indian Institute of Science, Bangalore. His research interests are in sparse signal recovery, energy harvesting based communication, performance analysis, and optimization of 5G and beyond communications. He has over 90 journal papers and more than 120 conference papers to his credit. He's an IEEE Fellow, Class of 2023, and a Fellow of INEE 2023. The next panelist is Dr. Radhakrishna Ganti. He's an Associate Professor at the Indian Institute of Technology, Madras, Chennai, India. He's received the 2014 IEEE Stefano Prize, Rice Prize and the 2014 IEEE Leonard G. Abraham Prize and the 2015 IEEE Communication Society Young Author Best Paper Award. He was also awarded the 2016-17 Institute Research and Development Award by IIT Madras. In 2019, he's been awarded the TSDSI Fellow for the technical excellence in standardization activities and contribution to LMNC use case in ITU. And the next panelist is Ramya. So T.R. Ramya is a principal research engineer in CIVIT. She focuses on the issues related to 5G, is also studying on the work scope related to 6G. Her research interests are in integrated sensing and communication and ambient IoT devices. She has about 15 years of experience encompassing academia, research, and industry. The last panelist we have is Vinay Srivastava. He is a general manager in telecom standards at Reliance Jio Infocom Limited, which is an Indian operator. Vinay's current interests revolve around next generation technologies such as non-terrestrial network, 6G waveform design, spectrum sharing, coexistence studies. He is part of current crucial national spectrum discussion committees. Vinay is actively engaged in standardization efforts related to ITU-R, 3GPP, and TSGSA. So I welcome all the panelists on board. And to begin with, what I'll do is I'll request the topic we are doing is emerging technologies for 6G. Most of the panelists must have already heard the 3 keynotes. So in lines with that, I request each speaker to give a small, about a minute and a half, 90 seconds to 90 seconds worth of brief on their perspective on the emerging technologies. So before we start with the questions, can I start with Dr. Ganti? Dr. Ganti, are you?
Yes. Can you hear me, Prakash?
Yes.
Yeah. Thank you, Prakash, for having me here. It's always a pleasure. So just my perspective on what are the possible technologies for 6G. The first thing I would say is full duplex. One reason is I have been working on it. Say, more than that, one of the main important things that we are seeing right now is that the spectrum in the sub 6 gigahertz band is completely congested. And whatever happened in 5G, we see that sub 6 is very critical. Okay, I mean that's the spectrum that's going to give you coverage. So in the lower frequency bands, full duplex is going to give you at least 1.8x or maybe 2x gains, and this is significant. I think already 3GPP has started studying full duplex in as a sub-band full duplex. Maybe over time it will become a full duplex solution. Hopefully that's one technology that's going to come in. So another thing that I see is the massive MIMO. Okay, people are now looking at, as the previous speakers have indicated, people are looking at spectrum in the 7 to 15 gigahertz range. So in this frequency, based on the path laws and other things, it's important that you have array gain, and that can be only achieved through massive MIMO solution. People are looking at thousands of antennas kind of thing. Okay, so while I have my own reservations on how to make this practical and economically feasible, I think this is one certain area that is going to play important, significant role. The third thing is the terahertz communication. Okay, there's a lot of activity in both academia and industry happening. Again, what I feel is terahertz is to 6G what millimeter was to 5G. Okay, so terahertz will be the new baby in the town, and there's lots of issues with it, and it will take us some time to stabilize that. But meanwhile, millimeter wave I think is getting mature right now. I think in a few more years, hopefully by the time we come to 6G, it can play some significant role. I think this is my short 90-second take on what is possible in 6G. I mean, I leave the floor to the next speaker.
Yes, thank you, Dr. Ganti. Vinay from Jio, could you give us your 90 minutes brief before we start questions?
90 seconds.
Yeah, thank you, Prakashji. I would be brief and quick here. I think a lot of eminent speakers have already put their perspective in last 2 days. As both as a technologist as well as part of an MNO, some of the key technologies which we look forward to in the future generation networks. One is better deployment with with enabling greener networks and better coverage. So RIS is definitely going to be one of the key feature for us. If and not to mention the possible or potential use of sensing more to improve the communication capabilities rather than as a ROI use case, replacing cameras. I think the other pain point which has been there is the power amplifier efficiencies, while the transmit power keeps going up, and the recent proposals on the use of artificial intelligence or machine learning to improve the DPD algorithms and have better PA efficiencies is something which might be very, very crucial. And last but not the least, the non-terrestrial networks, to ensure the continuity of services where cellular networks, the terrestrial networks cannot go. For example, the aircrafts, the marines, right? That can be a game changer. Yeah. Thank you.
Thank you. Thank you, Vinay. So now I move to Professor Chandra from ISC. So, Professor Chandra, your brief on what you think are interesting in the upcoming.
Yeah, so thank you once again for inviting me. So very briefly, I think the previous speakers have all really touched upon the most important aspects. But just to reiterate, I think new frequency bands will help to drive up the peak data rates. And in addition, on the other side, we want energy efficient communications. So energy harvesting based communications may be important. And thirdly, in order to improve coverage, one possibility or one thing to think about is very lightweight communication protocols, which can be implemented using low complex hardware and consuming less energy for again these kinds of sensing applications which require low power, low energy consumptions. And then on the technology side, perhaps the concept of cell-free or cell-less massive MIMO or MIMO communications. And also nowadays there is talk about the use of extreme MIMO, as Professor Ganti mentioned, communication using thousands of antennas. And correspondingly, one would like to use low resolution ADCs because otherwise the front haul bandwidth becomes very, very large. And also enabling better access technologies in massive machine type communications, specifically trying to perform the right trade-off between random access and scheduled access. And also last but not least, and also a topic not quite the last but one but not least again, is intelligent reflecting surfaces aided communications, especially in terms of ensuring uniform coverage. These RASs can potentially fill the coverage gaps and therefore provide more uniform coverage. And last but not least is machine learning and AI techniques and their role in improving communications and enabling communications plus X, where X could be compute, it could be control, it could be sensing, etc., is also going to be a key enabler of CXG. That's it from my side. Thank you.
Thank you, Dr. Chandra. Ramya, over to you. Your 90-second brief of what you think are interesting.
Yeah, Ramya here, and thanks Prakash for the introduction and giving me this opportunity. So having a lot of people said so many things on 6G, I would touch upon the main aspect of 6G to be the variety of services and how to seamlessly handle it. Like even in 5G, you wanted to handle EMBB, URLLC, and MMTC, but primarily 5G again became EMBB centric, so URLLC and MMTC didn't catch up. While in 6G, we want to make up for the gap. We want to look at more IoT kind of applications, making people's life more easier and safer, and handle things like added services like sensing, which is again for smart city kind of applications. And coming to high mobility scenarios. So how to seamlessly handle all these different scenarios from same cellular base stations, like whether it could be change in waveforms, change in modulation structure, or reference signal patterns, how to handle these seamlessly and with the aim of energy efficiency on top, and application of AML for these. So that is one thing which I think is also prime focus when we go towards 6G. Yeah, that's it from my side.
Thank you. Thank you, Ramya. So that was the free form answer. So maybe I'll now ask more pointed question. Okay. That is, in terms of, I think Dr. Gatti already told a list earlier, but I will reiterate. So what is it in 5G that was promised, which, maybe there some of the aspects were already talked about, millimeter wave and so on. So in 6G, what is it that you are seeing? The new things that were never there discussed in 5G, but the new concepts that you are seeing here, Dr. Ganti. This question is for you.
So, Prakash, in 5G, I mean, in specifically in 6G, one thing that I'm seeing right now is AI. I mean, as Professor Chandra pointed out, AML is going to play a certain significant role. Okay, whether be it on the receiver side to optimize your algorithms and for the receiver performance, or be it on the transmitter side for DPD. I think Vinay pointed this out for digital pre-distortion. I think AI is going to play some role. Okay, what exactly, I don't know at this point. There's a lot of debate whether the entire chains will be replaced by AML, but I don't think so. At least my personal gut feeling is that parts of the system are going to get replaced, and over time things will evolve. But I don't think I'll be comfortable to run a system where both the transmitter and the receiver are completely AI generated, and we don't know what is happening in there. Okay, so that's going to be one significant change. So other change, the other thing is about this waveforms, and what is the waveform that's going to be in 6G is still not clear. But after talking to a lot of people, I feel there's still this more juice left in OFDM to squeeze. I think it will be some OFDM based waveform, at least for most of the things, and some smaller additional waveforms may come on specific use case purposes. A significant difference from 5G that people are talking about is the terahertz communication. So where bandwidths are of the order of a few tens of gigahertz, and and spectrum is huge, and people are talking about terabits per second communication. There are test beds being built all around. Okay, and we have to see how the performance of these at this frequencies actually is. At this point, I believe it's a little bit too early and speculative to think about whether how deep terahertz is going to come into the specification. So, but there are implications on this. See, essentially, up to 4G, the bands are limited to sub 6 gigahertz, whereas in 5G we have introduced millimeter wave, and 6G people are talking about terahertz, and the bandwidths are slowly rising. So a single waveform, I don't think will be able to handle all these cases. So you're going to see at least a couple of waveforms, one for sub 6 and one for maybe the higher frequencies. And it's a nice study on how to switch between these waveforms and at what use cases you should shift. Okay, I think that's all I have for this question. Yeah.
Okay, thank you. Thanks for that. So the next question, I'll again go back to Vinay. So what are the current pain points in terms of 5G? 5G is already, even though it's early days for 5G, what is it that you are sensing as the operators around the world? Or what is it that they are feeling the pain in 5G, and what is it that desirable new things that they would like from the operator perspective?
Yeah, sure, Prakash. Thank you for that question. There are and then it's an involved question. I can talk on and on, but I will try to be brief again. Right. So firstly, the first issue, I think, which I already mentioned, is the limited power amplifier efficiencies, wherein we have active antenna arrays now with umpteen of power amplifiers mounted on them. So the effective power loss in the network is going up, right? Of course, the quality of coverage, and the fact that 5G no longer does an always-on transmission, even for SSBs, helps, right? But at the end, the percentage of power which you are wasting has gone up. Now, there are EMF and exclusion zone issues with 5G RUs because of the total EIRP, going up against 4G. These are the things which, of course, are some of the key challenges which future technologies should look at. The other, the crucial, the main pain point which I think the world has noted is the haste in choosing a particular spectrum, right? More towards FR2 or millimeter wave, right? So we saw that some of the earliest deployments of 5G were millimeter wave centric, and the MNOs quickly realized that the technology is not evolved, or at least the standards are not as evolved to support, for example, mobility at the beam management, for example, in release 15 was not mature to support mobility. The MNOs had to move down from FR2 to FR1 to have a more market centric deployment. Some of the geographies the MNOs had to give away FR2 spectrum. Things have improved now with the evolution of technology. However, still it's we would say that FR2 is not completely matured yet. We are looking at multi TRP and cell free kind of deployments to make sure that the non-line of sight limitation and airborne is taken care of. So that being said, some of the other things which I'll not explain but would just enumerate, which should be looked up, is one is the haste and standardization. I think release 15 was too quick to come up with a semi-cooked one with a non-standalone deployment advice. I think we can, probably in the future generations, we can spare more time on the first release itself to ensure that the first base release is mature enough to build your castle on it. Secondly, the correct choice of the elevated pitch use cases, the killer use cases as people used to call in 5G, right? Many of them have not taken up with the mass market yet. The XR is nowhere. We don't see it as a mass market use case. There are other verticals which were integrated, but I think the verticals didn't find it appealing to move to cellular based solutions. So it has to go hand in hand. The technology might enable many things, but you have to be very realistic about the market and the ROI which it is capable of. Then last but not the least, I think on TSDSI's front, we did an splendid job of submitting a writ which qualified IMT 2020 requirements. However, with the lack of homegrown equipment manufacturers support, we were not able to do much of the field trials. Forget about the deployments. Also, TSDSI couldn't support the evolution of these standards in terms of further releases. So these are, as within India, in our context, these are the things which we need to work on, and we need to ensure that we are more capable going towards the future generation, because the use cases of different geographies vary, and if we want our use cases to be taken care of, I think we should have local manufacturing capabilities in place. Thank you.
Thank you, Vinay. That was quite comprehensive. I'll now go to Dr. Chandra from ISC. So, Dr. Chandra, one of the things that's whatever is really new, and what I'm seeing is that the AI being discussed. Earlier, it was always AI as an application. Now, I'm seeing AI has become almost like the blood inside the veins rather than an external item. So what is it that makes AI so important or interesting? is it really that beneficial, or is it that the researchers have run out of ideas of algorithms to run on wireless, and now they are hoping for magic? You put all the data in, and hopefully the AI will magically solve our problems. I'm just throwing stuff in the air, but as a prof, maybe you can attack the problem that I'm posing.
Yeah,
Over to
thanks.
you.
Thanks, Prakash, for the question. And I'll start with the point that Professor Ganti mentioned, namely that the role that AI will play in 6G is quite unclear at this time. And my gut feeling agrees with his that certainly it's a far cry to expect that you have an AI-based transmitter and an AI-based receiver, and they will themselves figure out how to communicate with each other. While that is far away, I think a lot of entities, academia, as well as companies are already certainly experimenting with different types of AI-enabled blocks and trying to see what kind of benefits can be obtained. And the potential benefits could obviously be along the lines of the AI can help to fine-tune waveforms to account for different frequency bands, adapt to hardware vagaries like the hardware non-idealities, the channel related vagaries like the coherence time, coherence bandwidth, and so on. And especially in the context of communications plus X, where X could be sensing or computing or power transfer, etc. And the other promise of AI-enabled methods is that one may be able to avoid the costly and handcrafted optimization of hardware and algorithms by having a generic approach which essentially fine-tunes itself by using data that it collects over time. And thirdly, if one uses an AI-enabled solution, then maybe there is less standardization effort involved. One puts in a framework for an AI-based communication setup, but then since the AI is supposed to figure things out on its own, you need to you can be much more free in terms of what you're trying down based on using the standards. And further, at the end of the day, the role of a communication system is to provide a data pipe. And a lot of the comm system design is about trying to make this pipe more reliable, fatter, etc. But then the communications is actually being used for a particular application. And so by integrating communications with the end application for which the comm is being used, one can use AI ML techniques to perform end-to-end optimization. And so it's no longer just about this data pipe, but rather about what we will do with the data pipe. And of course, in specific blocks like the MAC layer, etc., you would want to resolve some of these long-standing tussles, which I mentioned earlier, which is contention-based versus scheduled transmissions, etc. And AI can potentially bridge this gap. But the verdict on all of these is not yet out. I think we still have a lot of work to do before we can say that, yes, AI can offer benefits, or maybe it's not worth the effort. So right now, I don't have a definitive answer. But it holds a lot of promise because AI has delivered fantastic results in many other fields. And so there's a priori no reason why it shouldn't do the same in comms.
Okay. Thank you. Thank you. Because a lot of times when the buzz comes in, Bitcoin was very big a few days ago. Everybody talked about it. Now suddenly nobody talks. So I'm not sure how much as a communication we have to invest, and how much of our, whether it's not about money, but all the psychological energies that need to go in, since we have limited resource. How much should go to AI and how much should go to something else is a bet everybody is, I think, calibrating, and we look for answers from experts like you. I'll now move to Ramya. So Ramya, one of the theme that seems to be getting discussed across is energy efficiency, overall end-to-end whenever we talk. Now, this is not new. It's been discussed in 3G, it's been discussed in 4G. I think when in 2G also they started talking about it. And but maybe I'll give you the floor and your comments on what is, one level they're adding a lot of features and a lot of demands on the network, which will require more energy. So what do you think was being done in 5G, and what is the expectation from 6G? So some thoughts from your side.
Yeah, thanks, Prakash. So energy efficiency, there's a lot of work going on in 5G, but the basic legacy system, it didn't start. I mean, it started primarily from release 18, network energy saving. So still, there are legacy UEs which may not be optimized for solutions involving network energy saving. So that's one drawback we still face. So if we have to cater to legacy UEs, the base stations should operate the way they have to. I mean, certain aspects of energy saving cannot be fully brought in. So energy saving mechanisms probably we can bring under two categories. Categories where we work at a UE specific level, and categories that work at a cell specific level. At currently most work have been done on UE specific levels, like reducing the number of ports or RS signals for a particular UE depending on the need or depending on the application. One enhancement here can be to application of AML. So since we cannot forego RS, so anyway we need RS for all CSM measurements, handover, beam management, etc. How can AML be brought in here so that we do prediction of the channel or future beams a priori, and so this may actually bring down the RS overhead or the power consumed in all those measurements and reporting and management. So that is at a UE specific level, the usage of AML. At the cell specific level, as I mentioned a minute back, we still have to support legacy UEs. So let's say a cell has a very few number of UEs. There's no way that it could hand over the existing UEs to the neighboring cells and completely switch off. I mean, this would actually lead to a lot of energy saving, but currently that mechanism is still not possible, because there could be idle UEs in the system which have to be served, and the cell, the BS has to still send SSBs regularly. All the SIB informations we cannot forego. So how to handle idle mode UEs, and is there any mechanism by which a base station, if not a macro, at least a small base station, can go for a complete shutdown when there are very few number of UEs? So that could be the thought for 6G from energy efficiency point of view.
Okay. Thank you. So maybe I'll have one more round of questions, a quick comments from each of you, because we are running now really.
Actually, Chair, we are over 5 minutes over, and we have to close the session because next session will start very soon. So,
so do we have one question each, one minute each with each?
I think we may get late. You may decide.
Okay. So maybe a quick points from each of you, since I've got such distinguished speaker. So small comments. Dr. Ganti, one of the thing I see new other than AI is integrated sensing and communication. Quick comment from you. Okay, what is it that you find interesting personally in this aspects, positioning, sensing, integrated sensing and communication?
So currently now what we have on our base stations are phased arrays, effectively 16 antennas, 32 antennas, or 64. So going forward, people are talking about 1,000 antennas. So technically, it's like a phased array, and you can do a radar kind of a thing, which is nothing but sensing. So people are looking at both sensing and communication together. However, we have to understand this from a commercial perspective also, to see what kind of accuracies you require in building these phased arrays. In building these phased arrays or this multi-antenna system, so that you get good positioning or good localization. That is something that's worthwhile studying before we get too excited on merging both communication and sensing. That's all. I mean, short answer from my side.
Okay. Another quick comment from Dr. Chandra. We've been hearing about this communication computing merger. So what is it that you see here? Does it, one trend we see is increased GPU usage, and the other side they are saying we are going to do energy efficiency and edge computing. Okay. So what is it that you are sensing in this aspects?
So, quick answer is basically that there have been great innovations and new technologies coming out both in the communication side as well as in the compute as well as storage side. And these innovations, one needs to see how these innovations will work together, and that is important anyway. And in particular, I think applications involving smart factories, mixed reality, extended reality, haptic interactions, connected vehicles, etc., will require these kinds of edge computing and try to leverage the innovations in computing and storage and integrate them into the communication networks in order to make those these highly demanding applications in terms of the user's quality of experience a reality.
Okay. Thank you. Vinay, your turn. A quick comment on, what we have seen is relays did work. D2D was getting talked about a lot. We have not yet seen much. Spectrum sharing is something we have not heard. NTN is something new. So your comments on these things, other than the traditional cellular architecture, what you feel
Yeah,
is coming?
I'll again try to be quick and brief. On relays, I think RIS reconfigurable intelligent surfaces are the best kind of relays in the shadowed regions, which I look forward to. Otherwise, also there have been use cases. There have been relays. Relays have been more in the shadow, or of the standard, more on sniffing the parameters as a UE and then retransmitting it, and with the network, the intelligent repeater support coming into 3GPP, and might get evolved to make the control channel for RIS in future. I think we are on the right path. The other one was NTN. NTN also, a lot of work has been done. I think the emphasis has been on service continuity, ubiquity, and scalability for multicast broadcast use cases. The problem, I think, is apart from the channel itself, which ends up into the kind of latency and the path loss which we see, is the price factor, right? We have to come up with cheaper terminals, and if possible, the same terminal which we use for cellular, if the same and inherently can be used for the non-terrestrial network as well, then that would be a market winning proposition, right? Now Leo has been one advent there, right? It allows you to come up with smaller terminals, and the channel impairments come down significantly, but then it brings in new challenges of moving cells and high dopplers. And I think as we go ahead, I think service continuity, access to consumer market, latency, throughput, and if we are able to successfully avoid the retransmissions on the physical layer, then probably we would have something on the plate. Last was the spectrum. It's I think it's a huge vast topic to be talked about in a single sentence, but WRC 23 is upcoming in November, and which is going to set up the agenda items for WRC 27, and various proposals have come in. I think 7 to 15 gigahertz spectrum range is the primary range, towards which several of the geographies want to conduct studies and see if IMT can coexist with satellite uplinks, right? If that is a possibility. However, similarly, many of the geographies have defense allocated spectrum there, which is a challenge. In my view, if we are able to divide the spectrum such that the mobility aided cellular communication can exist irrespective of which technology within FR1, say 7.125 gigahertz, and below, right? And the satellites can use the highest spectrum. That is one of the ways to go ahead. Or if we can come up with a waveform which allows a ground up work, of course, which allows both the satellites and the terrestrial network to reuse the same spectrum without any necessity of coexistence studies coming into picture, that would be something which we should look forward to. Thank you.
Okay. Thank you. Ramya, any last comments on IoT? We were hoping for big IoT rollout in 5G. I have not seen much. Your thoughts, quick comment on IoT?
Yeah, IoT was dealt both in 4G and 5G, but the main issue was it was like a miniaturized version of the legacy UEs there. I mean, NB IoT typically had all stacks of a normal LTE UE, whereas EdCap also had features of a UE with just some reduced functionalities. So that's why both of them didn't take up that much. So when it comes to 6G, since we want to use it for some sensors or inventory kind of applications, we need to support devices of much lower form factor and ultra low power consumption. So we have to in IoT we have to break the legacy and come with something totally new, a totally new waveform, a new way of synchronization, and yes, it's typically a bit a step forward from RFID. So RFID kind of devices, what they lack is the coverage and the security aspects as provided by any cellular system. So we want to club the functionalities that can be possible with RFID with the coverage and security of that could be offered in a cellular network. So that is one way forward which we should look into to bring in ambient IoT devices in 6G systems. Yeah, that's it from me.
Okay, I think I've sort of run out of time. I still had a lot of questions, so maybe we will have another session. Maybe we can accumulate all the speakers again and get together and do a longer workshop. So I'll now hand over to my co-chair. Rather than summarize the session, I think I'll give Priyanka for the concluding remarks, and Mr. Mittal for a vote of thanks. Priyanka, are you there?
Thank you, Prakash. I hope I'm audible.
Yes.
Yeah. So hello, everyone. I'm sure this was an enlightening session for all of us, and I thank all the speakers, the panelists, as well as the audience for making this session a success. So I think for the sake of time, I need to be very brief on the concluding remarks. So in this particular session, we got an idea of what we are expecting basically from a 6G network. So I think when we started off with the presentations, Mr. Jishnu, he gave a very good summary of all the technologies which will be used or which are the potential building blocks of a 6G network. And then we have had Professor Rahim talking about how the 6G network would be used to, for example, bridging the digital divide and solving the societal and economic issues that we are currently seeing in the 5G networks. And he also presented some very interesting solutions on how to improve the coverage aspects in a network without compromising on capacity or on network efficiency. And then we also had Mr. Hideaki talking about the various capabilities of a 6G network as compared to a 5G network, as well as the architecture and how there can be a smooth transition from the 5G network to a 6G network. And finally, we had the panel discussion where we got to know about the various perspectives of how a 6G network would look like, and also the operator perspective of what are the demands from a 6G network and what are the flaws that we are seeing currently in a 5G network which needs to be solved. So considering all these discussions and the questions which have been answered, in my opinion, I feel that so 6G network, it's not just about enhancing the 5G network, where, for example, if you have a throughput of 1x in a 5G network and I make it to a 10x throughput in case of a 6G network, and thus and in that way I enhance the network. So it's not just about that. It's about finding out what are the challenges that we are currently facing in a 5G network, and bringing in the academia, the industry, as well as the operators together to find the solutions to these issues and build a 6G network which will be able to address these issues, so that it enhances the user experience as well as it benefits the industries, the operators in terms of monetizations, etc. So saying this, I would like to conclude this session and also hand over to Mr. Mittal for the vote of thanks. Thank you.
Thank you, Priyanka. We had a wonderful session where we had the privilege of listening to distinguished speakers and panelists who shared their thoughts and enriched our understanding on emerging technologies for 6G. I, on behalf of TSDSI, would like to thank the co-chairs, speakers, and panelists for sparing their valuable time to be part of this session. I would like to thank all the participants for joining the session and enriching the proceedings with their insightful questions. I would like to thank Shweta, the session coordinator, TSDSI IT team, Marcom team, and the AirMeet tool support team for the hard work in organizing this session. Now we can take this session as closed. Thank you very much. Thank you all.